Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition. I'm up to problem 2.36. I'm going to do also 2.37 and maybe 2.38 in this video. So let's get on with it. 2.36 says, a hyperbolic Earth departure trajectory has a perigee altitude of 250 kilometers and a perigee speed of 11 kilometers per second. Calculate the hyperbolic excess speed, the radius when the true anomaly is 100 degrees, and the velocity radial and the velocity azimuth when the true anomaly is 100 degrees. So part A is the hyperbolic excess speed. Now, if you refer to my previous video on hyperbolic trajectories, you can get the equation for that. Which is velocity, well, we're at the periapsis, squared over 2 equals our gravitational constant over the radius at the periapsis, minus equals the velocity excess squared over 2. And we simply rearrange that for this and we get the answer. So the rearrangement of that is velocity excess square root of velocity periapsis squared minus 2 gravitational constant over radius periapsis. That's it. You work that out and you should get 0.849 kilometers per second. Part B is the radius when the true anomaly is 100 degrees. So this is also quite straightforward. We just have to work out the eccentricity, and that's easy because we have a formula for that, and that is actually a formula that is true for all orbits. So R equals the angular momentum squared over the gravitational constant is 1 over 1 plus E. Now we can get H because or the angular momentum, because we know the velocity and the radius at periapsis. So H is just RP times VP, which equals 7.29 by 10 to 10 kilometers squared per second. That would make sense, yeah. And then if we fill in the H there, we can get E. And we rearrange for E, which rearranged is H squared over RP times mu, and then minus 1. So, yeah, which equals 1.012. And then if we just put E back in there, we can get the radius when true anomaly is 100 degrees with the R equals H squared over mu, 1 over 1 plus E cos theta. So that's theta equals 100 degrees. And we put all that in, we get R equals 1.6179 by 10 to the 7, which is 6179 kilometers per second. And then part C is the velocity radial and the velocity azimuth when the true anomaly is 100 degrees. And that is also quite easy. So velocity azimuth is simply equal to the angular momentum divided by the radius, which turns out to be 4.5 kilometers per second, and velocity radial is equal to the gravitational constant over the angular momentum times E sine theta, which equals 5.45 kilometers per second. That is it. The MATLAB will be down below, and if you have any comments or think I've done something wrong, leave them in the comments below. I think I'll just leave it for this video. That took longer than expected. Thank you very much. Goodbye.